The second speaker is Fred Furtado from University of Wyoming, and he will tell us about scaling behavior of stochastic multiphase flow in porous.
Thank you. Yeah, I'm glad to mention that this work actually builds upon some work that Dan Marchesin did a long time ago, 1980. He was a young.
Who was the first thought?
Huh?
Look at the first thought.
Well, but you were a co-author, and you were working together, and.
I knew how to program.
Well, I don't know about that, but anyway, it's the same problem essentially. Is two-phase flow, and the idea is to understand the interface instabilities which are allowed by viscosity ratios, and here are some of the fingers computed by Dan and co-authors at that time, using the random choice method. That brought in some stochasticity, some random component to this problem. Then that excited the instabilities, and you see the developing in fingers. So this is what we did several years later, but essentially it's the same.
Now it's front tracking, right?
Yeah, there at that time was random choice, but this is not front tracking. Actually, this is standard finite difference methods. But anyway, so the idea is to understand this mixing in two-phase flow, and the mixing is a macroscopic mixing. Actually, it's the one fluid intertwines in the other one, and giving rise to these fingers. And this impacts in the amount of the resident fluid, which you can think of as oil, which is contacted by the displacing fluid, which is water. This is the water saturation. And this ultimately affects the amount of oil that is produced. And so the goal is to understand or try to understand the dynamics of this region, which I'll call the mixing region, where the two fluids are intertwined, and how it is affected by the underlying heterogeneity and the fluid instabilities. So this is the simple model. It's the simple two-phase flow, immiscible. There is no compressibility effects, and gravity is neglected. So S is the water saturation, so that is the displacing fluid. O is the resident fluid. And the fluids are essentially characterized by the viscosity ratios in the simple model, this parameter M, and the relative permeability functions, which define the flux function, are quadratic. And there is this random field, which is the absolute permeability. The idea is the permeability is highly heterogeneous, and you see variations over several length scales. And then the idea was to model the absolute permeability as a random field. So those equations are well, you have a conservation law, a hyperbolic conservation law for the saturation, and an elliptic equation for the pressure field, and they are coupled. And this coupling is what allows the fluid instabilities to manifest themselves, and then those instabilities, when excited by the underlying heterogeneity, they develop into fingers, and then the fingers grow, and the nonlinearity takes place in trying to control this growth, and interacts with the heterogeneity. So that is the the underlying mechanisms. And the goal is to try to understand how they combine to give rise to the dynamics of this mixing region. So let me say a few words about the permeability field. It is a simple model that takes the permeability field as a scalar field. It's a log normal field, so it's the exponential of a Gaussian, and this Gaussian has mean 0, and the covariance function decays as a power law. The idea here is to allow for very long range correlations in the heterogeneities, and so this exponent beta controls the rate at which the correlations decay. So as beta increases to 0, the longer heterogeneity occurring in larger length scales are emphasized, and the field becomes smoother locally, and the opposite happens when beta decreases. And so there is, in addition to this beta characterizing the geology, there is this parameter rho, which essentially controls the overall strength of the variations. So by changing rho, you can control the size of the fluctuations of this random field. So essentially then you have 3 parameters in this model. One for the fluid, which is the viscosity ratio. So this parameter characterizes the fluids completely. And you have the exponent beta, which controls the degree of the correlation of the heterogeneities. And you have the strength of the fluctuations, which is essentially dictated by the value of rho, but a better way to quantify it is in terms of the coefficient of variation, which is the ratio of the standard deviation and the mean value. So these are the 3 parameters that play a role in this model. So here's just some two realizations of the random fields. The one above is with short-range correlations. Essentially, the limit as beta goes to minus infinity. And the other one is displaying longer range correlations, which is beta minus 0.5. And those will be the 2 ones discussed in this talk. A quantitative analysis of the mixing region is afforded by looking at the mixing length and seeing how it evolves in time. And to define the mixing length, we analyze it in terms of a model problem, which is this linear convection diffusion equation, for which we can solve. There is a similarity solution in terms of the complementary error function. And this similarity solution identifies 2 important length scales. One is the distance traveled by the mean position of this diffusion layer, capital L, and the other one is the mixing length, which is the extent or a measure of the length of this mixing region, so where the fluids mix. It turns out, I will not go into details, but that mixing length, which is part of the solution, can be obtained in a different way by simply comparing the mass distribution of the problem with diffusion nu and the problem without diffusion. So if you suppress diffusion, it's a simple hyperbolic problem. The layer separating the 2 fluids simply displays, travels in time. And so if you measure the difference of this solution to the solution with diffusion, this difference is related to the mixing length, which is defined by the similarity solution in this way. Okay? This procedure actually can be carried over to the nonlinear problem, for which we don't have such a self-similar solution explicitly. But we can use this then to define a mixing length and study its evolution for the nonlinear problem. So this is what we do here. So S now is a saturation of the 2-phase flow, the water saturation. So if you average in the transverse direction, so like when we had here, you average in the transverse direction the saturation to give rise to a one-dimensional profile, and you average over all realizations of your random field, then you can use this one-dimensional profile and compare it with the Berkeley-Leverett solution, which is simply the solution of the problem with a homogeneous field, underlying heterogeneity. Then this difference defines the mixing length. Okay, so that is motivated by this relation between the mixing length and the mass distribution. So this is what we take as the mixing length. It's this average here is a random variable still, because you're simply doing this, this one. You're simply doing the spatial average. So then you average over the ensemble to define the mean saturation profile, and then from there you compute the mixing length. So, and then if you plot it in log-log scale, so this is the mixing length versus travel distance, which is equivalent to time. So there is a linear relation between the travel distance of the mixing region and time. So if you plot it in log-log scales, so what you see here, several curves are for the individual realizations, and the dark curve is just the average of over those realizations, and that is the mixing length of the ensemble. So the slope of this line gives you the rate at which the mixing length is growing in time. So in other words, it gives you the exponent of the scaling law that describes the dynamics, the large time dynamics of this mixing length. Okay, so here is the one example for the uncorrelated field, beta minus infinity. Essentially, it's the uncorrelated field, so short-range correlations, and this is for the long-range correlations. Now, there are two mechanisms, the heterogeneity, the underlying heterogeneity, and the nonlinearities. To understand the heterogeneity alone, you take the linear transport, so the tracer flow problem, which is neutrally stable, so that the interface is neutrally stable. And so consider this problem with this the random permeability fields. And so in the past, primarily Gleim and the co-authors, they analyzed this problem and came up with a perturbation theory, several different perturbation theories, plus numerical simulations that, among other things, they retained an effective equation that describes the mean saturation for this problem. And the effect of randomness translates into this, to lead in order, into this diffusion operator with a diffusivity which changes in time, and it's given by this integral along the streamlines of the correlation of the velocity field, of the fluctuations of the velocity field. And from there, they obtained there's something like a phase transition, so a critical value for the exponent beta of the random field, that controls the correlation. If beta is less than -1, so if it decays sufficiently fast, then eventually this nu of t is stabilized, and you get the standard diffusion equation, the Ficken diffusion. But if beta is larger than -1, so the critical value is beta equals -1, then the diffusion never stabilizes, and the diffusion is anomalous, so meaning that it grows with an exponent which is larger than 1/2. So 1/2 is the exponent of a Ficken diffusion process. The distance scales as the square root of time. And in the case of beta bigger than -1, so the exponent is, so it's a super diffusion. It diffuses faster than Ficken. So here are comparisons for the two different values of beta infinity and beta 0.5, comparison of the two different perturbation theories, and numerical simulations, and the agreement is quite remarkable. And for several different strengths, so varying that parameter rho, which changes the strength of the fluctuations of the random field. So this is then the effect of heterogeneity alone. So you have this dynamics of the mixing region controlled by those exponents. If you now look at you take the random, the randomness away, look at the homogeneous case. K is just a constant, but now look at the nonlinear problem. A linear stability analysis identifies this as the parameter that points to the transition of the stable to unstable regime. So that is the frontal mobility ratio. And if lambda is bigger than 1, so you have an unstable regime. So perturbations will develop into fingers. And lambda less than 1, you have a stable regime, and those perturbations will decay. And if you look at the long time behavior of the instabilities once they are excited, then you obtain that in this regime, which is the nonlinear regime, the mixing length, grows linearly in time. And in the case of the stable regime, it does not grow at all. And so this parameter here can be, or the critical value lambda goes to 1 can be related to the viscosity ratios, and for the choice of permeability that we showed, the viscosity ratio which corresponds to the critical value is this funny number here. Now, before we go and look at the combined effects, let me point out that there is some, so the whole problem is actually a scale invariant in the following sense. So if you think of the permeability associated with this parameter rho, which controls the degree of or the size of the fluctuations, and if you exploit the fact that the covariance has this fractal behavior, it's just a power law, then you see that this Gaussian field satisfies this similarity relation. So if you rescale space in this way, where beta is that exponent, then the field that you get is the same as the original field, but multiplied by alpha. So in other words, this is a self-similarity in the probability sense. So this is a quality in law, probability law. So have the two fields are the same in law. So if you exploit that, this similarity, and the fact that these equations are also scale invariant, then what you conclude is that if let's say P subscript rho 2, V, rho 2, etc., are solutions of this equation when rho equals rho 2. So if you rescale them in this way, what you get is the solution of the same system with rho equals to rho 1. Okay? So this is in the sense in that this problem is scale invariant. If you rescale properly, you can obtain a solution of one problem from the solution of the other one. Okay? Yeah, this is rho 1, right? So if you take the solution when rho equals to rho 2, so you have this V, P, and S, and rescale them in this way, then the resulting V, P, and S satisfy the same problem, but with rho replaced by rho 1. Okay? So you have this scale invariance, and this, if you carry on and look at the consequence for the mixing length and the mean saturation profile, what you get is that the mean saturation profiles for different values of rho are related in this way, and the mixing lengths or the corresponding mixing lengths are related in this way. So one way of looking at this is like this. Suppose that rho 1 is larger than rho 2. So this field is more heterogeneous than this one. So then sigma 1 is larger than sigma 2. So this ratio here is less than 1. and this is bigger than 1. So it's as if you're changing time. So there is something like a relativistic effect here. So the development of this, the mixing length for a stronger heterogeneity takes place over a much longer period of time. So as t, let's say, varies from 0 to 10 here, over here it would vary from 0 to 1. So whatever happens for the weaker heterogeneity over a smaller time interval will happen for the more heterogeneous one, but over a longer time interval. Plus, you have to rescale it, so you have to account for this, so the size of the mixing region also changes. So if sigma 1 is larger than sigma 2, so it's as if the development takes place over much longer time or longer distance traveled, and the size increases. Okay? So if you take those scaling relations and apply to the simulations that were performed, you see a very nice matching. So what you see here is for the tracer flow problem. These are the mean saturation profiles at different times for different permeability strengths. So the parameter rho was chosen so that the corresponding sigmas are related as follows: 1, 1/2, 1/4, and 1/8. So the blue one is the strongest one, and that corresponds to the value of sigma equals to 1. So if you rescale the blue one by a factor of 8, then you get this black one. If you rescale the green one by a factor of 4, you get the black one again. In other words, if you apply that scaling to the 4 different profiles which were computed using different permeability strengths, then they all collapse to a single profile. So what that says that if you understand one profile, I mean for one specific value of the parameter rho, then you understand for them all, because it's just rescaling. And the same apply to the mixing length curves. I mean, these are the different mixing length curves plotted in log-log scale. These are the different heterogeneity strengths. If you rescale them according to those laws, they collapse again to a single curve, except at short distances where you no longer have a fractal random field because of its realization on a grid, and also you have a numerical diffusion that disturbs the result. But over most of the region, you have a perfect match of the mixing length. And this is another issue. If you look at the mixing length asymptotically as t to the power gamma, gamma is the exponent that controls the growth, but with this prefactor a, which depends on rho, then those scaling relations also imply that in the case of beta equals to 1/2, you would have a relation among the a sub rhos, the prefactor, as follows. So a sub rho over a sub 1 scales with rho. And what you see here is just this plot confirming that. The horizontal lines are the different values of rho, and the other curves are just those ratios with a reference one, and they all approach the asymptotic value. That was for the tracer flow. The same happens for the nonlinear two-phase flow. So this is the case where the neutrally stable with respect to fingering. The viscosity ratio is this value. So these are the saturation profiles at the different times for different permeability strengths or fluctuation strengths. And then when you rescale them according to those laws, they all collapse to a single curve here. And the same for the mixing lengths. When you rescale, they all collapse. This is for a more dramatic case in which the viscosity ratio is 20, so this is in the unstable regime. You have again the saturation profiles, the mean saturation profiles at different times for the different permeability strengths, and collapsing to a single one. And the same for the mixing length curves. They collapse to a single one. And so essentially, when you look at this sort of phase diagram, you see here the different viscosity ratios, here the different permeability strengths, fluctuations. And what you see again is a confirmation of, or another way of looking at that. For instance, if you look at one value, as we are doing computations in a finite domain, so you don't have enough time for the asymptotic behavior to develop. But as you reduce the strength of the fluctuations, you see the heterogeneity being dominating, but then eventually you have a crossover to the nonlinear regime as time goes on. And so you see here that change. So this is corresponding to beta equals to minus infinity. So the theory predicts that gamma is 1/2, and you have a very good match here. There is an underlying line with slope 1/2 here. But as you reduce the strength of the fluctuations, this cross over to the nonlinear dominated regime, which has exponent 1. So in summary, you have different linear regimes. I mean, for the linear transport problem, you have the Fickian and the anomalous case. In the case of nonlinear flow, nonlinearity always dominates in the end, and you have two possible regimes depending on whether it's unstable or stable. And if you have a heterogeneity strong enough, in an early stage, the heterogeneities dominate, and both nonlinear and linear flow behave essentially the same regarding the dynamics of the mixing region. But eventually, nonlinearity dominates, and then you see this crossover from heterogeneity control to nonlinear controlled mixing. I'd like to finish by wishing Dan well and anticipating many more years of your vigorous and important contributions to science and training of young scientists. Thank you.
You mentioned the results of the perturbation. You mentioned the perturbation was the random component was considered as a perturbation.
That's right.
And if you remove completely the random component, it's still fingering.
In the nonlinear case.
In the homogeneous.
Yes, you have to. That's right. That's right. If you just perturb initially, and if you're in the unstable regime, they will grow and you see the fingers.
And just to understand, what determines there is a most unstable, linearly most unstable scale? So
not in the hyperbolic case. All scales are unstable. They all grow exponentially. I mean, that is the linear.
Exponentially, but it's not ill-conditioned.
It is actually. So you need. That's right. You need some diffusion to sort of introduce a cutoff of the wavelength, which grows unstable. But so in the case of the simulation, it's provided by the numerical simulation. I mean, by the discretization.
So is in spirit similar to Rayleigh-Taylor or kind of instability? Or it's similar to the instability when you have
heavier fluid on top of
So if you have capillarity, do you think this is going to change much?
Not really. The only thing that changed, what he alluded to, is that not all wavelengths now are unstable. Actually, we started this study with capillarity in, and we realized that nothing changed, so we removed it. Of course, it provides a little more, it stabilizes a little bit, but only to the extent that it stabilizes some of the modes, not all of them. So you always have some unstable modes, even if you have, if you account for the dissipative associated with capillarity. But
well, Hans was first, but you will.
So there is, of course, in the 80s and 90s, a lot of work was done in stochastic random fields by guys like Galvar and all these guys.
Right.
And you have extended that now to give an analytic expression for this. This is absolutely, it's very interesting actually. That's what you have added to.
in the case of this fractal random field, yes.
You use a fractal random field?
Yes. So fractal in the sense that the
Power law variable.
exactly, yes. But decays, not increase, but decays.
Okay.
Yeah. And then you have all those analytical
And
expressions.
you can do it for immiscible, and
Yes, because the same scalings, I mean, can be exploited, yes.
interesting.
I wanted to ask if you can make contact with physical experiments, and like is the fractal assumption a decent one for porous media, and do you get these behaviors?
There is no justification, I mean, no geological justification for that. We've seen some data that it models reasonably well, at least over a range of length scales. This fractal assumption models well, but that's it. More generally, you should look at perhaps a better model would be a multifractal field in which what you have is the exponent that controls the decay depends on the length scale. It's not a fixed number as in the fractal case, which decays with that fixed value. But if you allow it to vary with length scales, then you have a better description of the geology. But asymptotically, you should see a similar result.
No questions? So let's think further again.